Because when QB hat lambda equal to 0, then delta phi is of order phi, so that's the signature that lambda generates a global symmetry. Okay. But that does not necessarily mean that the delta phi tilde is 0, because delta phi tilde is still there. Okay. So its constant piece doesn't vanish. Okay, and the question was, what do we do about this? Okay. So let me give you two answers to this. One is a general answer, okay, which doesn't require any further assumption. General answer, okay. And that is based on the observation that this combination, okay, is BRST trivial. Okay, so let's see QB on QB lambda tilde plus K lambda. Okay, QB square of course is 0, so this gives you QB K lambda, but QB K lambda, okay, by one of the identities that I wrote down earlier is minus K QB minus KG K on lambda, okay, because QB K plus K QB plus KG K was 0, okay, as a consequence of the general identity and the fact that the psi vacuum satisfies its equation of motion. So this is nothing but minus K QB hat lambda, and hence this is 0. Okay. So this just says that while the shift in phi tilde is not 0, okay, it's a solution to the equation that QB on this is equal to 0. Okay, so the shift in phi tilde, okay, is a solution to QB phi tilde equal to 0. Okay. And as we had discussed in the context of equations of motion, okay, that when you solve the equations of motion, the equation of motion for phi tilde, okay, for a given phi allows you to add arbitrary solution to QB phi tilde equal to 0, though, and that's the only degree of freedom that phi tilde has. Okay. So while what we are saying here is that while delta phi tilde is not 0, okay, this is something that automatically satisfies the linearized equation of motion for phi tilde, which is QB on this equal to 0. Okay. And then we had also seen that this particular, whatever you add to the solution for phi tilde doesn't affect the equation of motion for phi, because the equation of motion for phi was completely independent of phi tilde. Okay. So this says that even though we make a shift in phi tilde, okay, this has no effect on the interacting part of the theory. Okay. So even though it looks like that under this gauge transformation, okay, phi transforms as if it's a global symmetry, phi tilde transforms as if it's not a global symmetry because there is a constant shift, but that has no bearing on the interacting part. And as far as the interacting part is concerned, this transformation acts as a global symmetry transformation. Okay. And we saw a consequence of that, because just by using QB hat lambda equal to 0, we proved the word identity. Right, that for example, bosons and fermions have the same mass and same decay weight. So that's the general answer to this question. Now I'll give a special answer, okay, which in fact is very general, because I think all known cases fall in this category. And that is the following, that we have to solve this QB hat lambda equal to 0. Okay. But what one often finds is that the solution to QB hat lambda equal to 0, okay, has the form that lambda is G on A, on some state A. Okay, G, let me remind you, is of course identity in the NS sector and the zero mode of the picture changing operator in the Ramon sector. And QB tilde on A is equal to 0. Now it follows as a consequence of this that QB hat lambda is 0, right? Because this implies that QB hat lambda is equal to QB hat G A, okay? But this we know is G QB tilde A, okay? So as long as QB tilde is 0, So if lambda has this form with A satisfying this equation, then this is automatically satisfied. Okay. So suppose lambda has this form. Okay, and then let's go back here again. Okay. So then this combination QB lambda tilde plus K lambda, this has the form of QB lambda tilde plus K G A. Okay. Now choose. See, lambda tilde is completely arbitrary, but now I'm making a choice of lambda tilde. Choose lambda tilde equal to A. Okay, A is in H tilde, right? Because G changes the picture number. If you choose lambda tilde equal to A, then this becomes QB on A plus K G on A, which is just QB tilde on A, and this is 0. Okay. So what I'm saying here is that if lambda has this spatial form, okay, which as I said is true in all known examples, if lambda has this spatial form, okay, then by appropriately choosing lambda tilde, okay, which is A, lambda tilde is to begin with was an independent parameter. By choosing lambda tilde to be A, okay, we can ensure that delta phi tilde is also 0. Okay, this is a shift in phi tilde. Okay, so then this becomes a genuine global symmetry both in the interacting sector as well as in the free sector. Okay, in the other case, it's a global symmetry in the interacting sector. It's not quite like a global symmetry in the free sector, but that has no effect back on the interacting sector.
You're looking at a reduced space of gauge transformation, where the lambda and lambda tilde are not independent gauge.
That's right, yeah. Because you are trying to identify global symmetry, right? So global symmetry already lambda is restricted, right? Not every lambda is a global symmetry. So the genuine global symmetry will be that you fix lambda to be whatever it is you get by solving this, and at the same time you also choose lambda tilde to be this one. Because clearly for not every lambda tilde it will be a global symmetry, right? Because otherwise this QB lambda tilde term will always be there, right? So you have to choose lambda tilde, right? Naively you would have thought that you will choose lambda tilde to be either 0 or something which is BRST trivial, right? Now what I'm saying is that you choose lambda tilde to be A, right? You can of course add some QB on something, and that's what corresponds to a global symmetry in the free sector.
Your earlier answer, because in a sense there was no reason for phi tilde to be invariant.
I agree, because I mean normally you would call something a global symmetry if all fields transform beginning with linear term, right? Here that is not necessary because phi tilde is a decoupled sector, right? So even if it gets shifted, it has no effect on the interacting sector, right? So that's why you don't really have to do this. The general answer is good enough. Okay. But I'm just saying that in
you could realize the global symmetry
also in the free sector,
the full theory.
Yeah, by appropriately choosing lambda tilde. But it's certainly not necessary because we derived the word identity yesterday, right? For the Bose-Fermi equality, for example, right? And there we had no, the fact that this is not 0 played no role, right? Because the interacting part of the theory only depended on the QB hat lambda equal to 0 equation.
So in particular, the free sector may not have Bose-Fermi, need not have Bose-Fermi.
Exactly, yeah, yeah. Well, free sector is free, so it has Bose-Fermi degeneracy, you already know.
Oh, because
right?
it has the free spectrum.
Exactly, because it has a free spectrum.
Which already has.
Exactly. Okay, so this was the answer to yesterday's question. So now we turn to a somewhat different topic. Okay, so what we have done so far is to describe the construction of string field theory, and I also described the systematic procedure for how to use the string field theory to calculate renormalized mass and S matrix and so on. Okay. So our goal now will be to try to prove eventually that this S matrix that we get this way is unitary. Okay. But for this you have to develop some machinery, and that's what we want to do today. Okay. So this is what I'll call string field theory in momentum space. Okay, we now try to understand how the Feynman rules of this theory look in some more detail. Okay, so let me begin by recalling the structure of the vortex. Okay, that is this what we call. Now I have gone back to the actual vortex, not the 1pi vortex, okay, but the original Feynman rules. Okay, because you build the 1pi graph from the original Feynman rules, and the reason that you don't want to start with the 1pi vortex is because 1pi amplitudes already contain part of the imaginary part, right? And the whole idea of unitarity is to identify the imaginary part. Okay, so you really have to start with the original vortex, which has no imaginary part. So this is integral r bar gmn omega gmn 6g minus 6 plus 2m plus 2n now each AI, okay, is some off-cell state in the theory. Okay, so AI is some off-cell state which is in H hat t. Okay. And the general feature of this AI, the general structure is that it has this e to the I ki dot x. Okay, that fixes a momentum that this vortex operator carries, and then some times oscillators. Okay. So the structure of this is that this can be written as integral okay. So I am writing down some part of this correlation function. So this, if you recall, what is this? This is obtained by calculating some correlation function of these vortex operators, right? With some additional ghosts, picture changing operators, everything inserted on this. Okay. But let's focus on the contribution from this part. Okay. So this part has the structure of exponential minus, let's use some other symbol, not A, let's call it G. This is not the metric, okay, just some matrix which I'll describe times okay. So what is t? This t is the coordinates on r bar gmn. Okay. So this exponential, okay, so this part, this factor comes basically from the correlation functions of e to the I ki dot x. Okay, if you remember the correlation function of e to the I ki dot x on the Riemann surface, okay, it always has a factor which has this structure. And then of course you can have polynomials in momentum, because you can have, for example, derivatives of x in this oscillators, right? You can have the alpha oscillators, which when you calculate the correlation function, it will bring down powers of momentum. Okay. But our main focus will be on this part. Okay, there's an exponential part which comes basically from the Green's function, okay, of the x's, okay, which comes. So basically you will get a ki dot kj times the Green's function of x of zi times x of zj. Right? Though zi and zj information has gone into the t, because this is the full set of coordinates on r bar gmn, and this is the structure. summed over? Yes, it's summed over G. Yeah. Okay, but for each genus, you have a structure like this. Now, the claim will be Gij of T is positive definite. More accurately, I would say this can be made, instead of saying it is, I can say it can be made. It can be made positive definite. Okay, and in fact, those are the, and it can be made positive definite by suitable choice of this R bar GMNs, okay, by exploiting the freedom of choosing local coordinates at the punctures, which in turn affects the choice of R bar GMN. Okay, and this is precisely what we described earlier as adding stubs. Okay, this is done by adding stubs. Okay, because what does adding stubs do, right? Adding stubs minus log 1 over lambda I ki square plus mi square. Okay, in general, of course, there are other contributions. Okay, because it need not be a primary, right? This is one part which comes from the conformal dimension, but there are also other contributions, okay, which reflects the fact that this is not necessarily a primary state, but this is the main focus. So the idea is that by taking lambda I to be sufficiently small, we can add to the exponent, okay, a large diagonal term, and by making the diagonal term large enough, you can make this Gij positive definite. Okay, this is the fact that by, as I said, adding stubs corresponding to integrate out the heavy modes. Okay, so the effective cutoff, effective UV cutoff will come down. Okay, effective UV cutoff coming down means that you should multiply this k square in the exponent by a large amount, right? Because that's what brings down the effective ultraviolet cutoff. Okay, and that's what is happening here. Is this point clear? Okay. So this immediately tells us, because of these exponential factors, that loop momentum integrals are UV finite for spatial momentum integral. Okay, because if this is a positive definite matrix, then for large spatial momentum, it's exponentially suppressed, and the polynomials, of course, cannot overcome this. Okay, so you never get any divergence from the large momentum region. Okay, so this is one explicit way of seeing why you get ultraviolet finite answers from string field theory. Yes, this is true for Euclidean momentum, right? So I'm now coming to problem with the Lorentzian momentum. So the problem comes is the exponential Gij of T Ki naught Kj naught factor. Right, because you can see that Ki dot Kj, the time component here, will be it will reverse the sign. You will have Gij of T Ki0 Kj0, okay? And this of course grows exponentially. This grows for large Ki0. Okay. So this shows that we will be in trouble if we try to define the loop integrals in the standard way, okay, where we take both the spatial loop momentum integral as well as the time components of the loop momentum integral along the real axis. Okay, because if we try to integrate the loop energies along the real axis, okay, the integrand will diverge exponentially. Okay, and that clearly is not acceptable. Yes.
Last series of talks.
Yes.
Had a way of writing down these Schwinger parameters and then converting into an expression which is vector everywhere.
Well, there the problem is that you will find that you can write in terms of Schwinger parameters, right? But then the integral over the Schwinger parameters will diverge.
Yes, but there was an alternate way of.
Yes, by turning the Schwinger parameters in a complex direction,
yes.
Right? That's what I described in the first lecture.
It seems like we have gone back to the Schwinger parameters. Why are we getting a divergence?
Well, so because we are not following that procedure now, right? Because that was given as an initial motivation that that's one way you could make this finite, right? But now I'm thinking of this as a regular string field theory, right? You have to treat this as what you would do in a normal field theory, right? Because we could try to use that prescription now, that instead of trying to integrate over momentum, you first convert it to Schwinger parameter, right? And then define the Schwinger parameter integrals by turning this in the complex direction. Okay? But based on that procedure, right, proving unitarity becomes very hard because you don't really have a good handle of the momentum integrals, right? So what we will do now is to work in the momentum space method, right? But what one can show, okay, and I'll not show this, but it's a straightforward algebraic proof that the procedure that I'll be describing now, okay, is equivalent to turning the Schwinger parameters in the complex direction. Okay, that you take each Schwinger parameter and instead of running it to infinity, you turn it towards I infinity, okay, at some point. Okay. In other words, if for every propagator, for example, instead of defining it from 0 to infinity, you will do the integral from 0 to I infinity. Okay. But as I said, based on that procedure, to prove unitarity seems very hard. Okay, so we'll try to do it directly in the momentum space from Euclidean amplitudes. Okay, but I'll try to give a more detailed procedure for what this means. Okay, so here is the procedure that will follow. Okay, and in that process we will also see the difference between ordinary field theories, okay, the weak rotation in ordinary field theories and the one that you have to do in string field theory. Okay. So the first, what we do is that we multiply all external energies. External energies mean energies of external particles, okay, by a common complex number u. Okay, this procedure doesn't quite work if you choose independent complex numbers for each external energy. Okay, but we don't need to do that. We multiply everything by a common complex number u, which means that the moment of the external states you take to be of the form uai, ei. Okay, ei is at the physical energies that you are interested in, okay, and pi, the spatial momentum. You never touch spatial momentum. Okay, they are always real. Okay, so step 2 is that for U imaginary. Okay, this is where we begin. We take all loop energies to be imaginary. Okay, so each loop energy integral runs from minus I infinity okay, just along the imaginary axis. Okay. And here you can easily convince yourself that the integral is perfectly well defined, okay, because for example in this case all internal lines, internal and external lines carry imaginary energy. Okay. So the vortices carry exponential suppression. Okay. And furthermore, ki square plus mi square inverse never diverges. Okay, because since it's so what is this? This is minus ki0 square plus ki square plus mi square. Okay, so this is positive, and this is also positive because ki0 is purely imaginary. Okay, so in this case the integrals are perfectly well defined. Okay, the poles are away from the integration contours, and as you go towards infinity along any of the integration contour in any of the directions, the integrand is exponentially suppressed, so the integrals are well defined. Is this point clear? Okay. So now the step 3 is to take U to one limit along the first quadrant. Okay, which means that if this is a U plane, okay, you start from somewhere on the imaginary axis and choose some contour and come to 1. Okay, but you choose the contour by along the first quadrant. Yeah, you can choose it in negative energy axis, but you have to go towards positive and then come down. Yeah, exactly. You go towards positive along the imaginary axis because you don't want to leave the first quadrant. Well, you can go a little bit here and come back, that doesn't matter, but you shouldn't go like this, for example, right? That will give you the wrong answer. Okay, so the idea is that we will take the original result, the Euclidean result, okay, and try to define the result for u equal to 1, okay, by analytic continuation of the original result, okay, because you can think of this as an analytic function of u, which is at least well defined on the imaginary axis. Okay, and now we will try to take the analytic continuation, okay, as u approaches 1. Okay. But we want to see what it means in terms of momentum space integral directly. Okay, so let's see what would happen as you start deforming u. So for in loop energy space, the loop momenta are always along the real axis, nothing much is happening there. Okay, but in the loop energy space, what is going to happen is that as you take u and start moving towards 1, okay, the locations of the poles, okay, which are coming from these factors, okay, These of course depend on u, right? Because each ki depends on external momentum. Okay, so in the loop energy space, the locations of the poles depend on u. Okay. And what may happen sometime is that the pole may come towards the imaginary axis, which is the original integration axis. Okay. Now, you have two choices as the pole comes towards the imaginary axis. You can let the pole cross. Okay. But if you let the pole cross, then there is a discontinuous jump. Okay. And that means that this is not a correct analytic continuation. If you are trying to define the function as an analytic continuation of the original result, you are not allowed to do this discontinuous jump. Okay. So the procedure that one follows is that if a pole approaches a given loop energy integration axis, okay, you deform it away from the pole. Okay, so suppose the pole crosses, okay, you basically deform the contour away from the pole, okay, even if the pole has crossed the imaginary axis. But the endpoints of the integration contour, okay, you keep fixed at plus minus I infinity, because if you, for example, one procedure will be to rotate the contour. Okay, in fact, that's what you do in standard field theory, that you always choose the contour integrals, okay, the phase of the contour integral to be the same as the phase of u. Okay, so as you are rotating the external momentum, you also rotate the external loop momentum, okay, to be along the same, to have the same phase, so that as when the external momentum comes to the real value, okay, the loop momentum, the loop energy integrals also run along the real value. Okay, that's the standard field theory. But that you know you cannot do, because if you try to do that, if you try to rotate the contour, okay, then once it has gone beyond 45 degrees, okay, the endpoints, the integral will diverge at the endpoints. Okay, so that is ill-defined. So you try to keep the endpoints of the integration at plus minus I infinity, but in the interior you deform the contour. Okay, we deform the contour to avoid poles. Yes.
Poles are the poles of your original integral with as a, I mean, as you're moving u, then this pole is moving.
Exactly. Yeah. So the point is the this ki, right? So let's see each ki, okay, is a linear combination of the Li's of L's, which are the loop momentum integrals, and P's. Okay. The point is the P's are changing as you are changing u, right? And as a result, the L plane, in the L plane, the poles move. Okay, later on I'll give a specific example where it may become clearer, but you can see already that this integrand, these factors are functions of L and P. Okay. So in the L plane, the location of the pole depends on P, right? And as P is changing, the pole is moving in the L plane, and it may happen that the pole is will come towards the imaginary axis. Okay. If it happens, then you have to deform the contour away from the pole. Is this point clear? Okay. And you keep deforming it, okay, till you reach u equal to 1. Okay. So ultimately you have to define the value, the desired value, which is the value at u equal to 1, as a limit of this process, okay, as u goes to 1. Endpoint is 1, u equal to 1.
That maybe that the pole may pull the contour quite a bit.
Yes, that's right. Yeah, it doesn't matter. Okay. So keep doing it till we reach 1. Okay. Now it's not obvious that this can always be done. Okay. So let me see how it could fail. Okay. So let's imagine that this is, take one particular loop energy integration contour. Okay. And suppose, okay, that we have a situation where as you are moving u, okay, one pole comes to the loop energy contour from one side and the other pole comes from the other side. Okay. It's approaching the loop energy contour from opposite directions. Okay. And then you can see that it's not possible to deform this away from both poles. Right? If the two poles approach each other from opposite sides, okay, then this contour is pinched, okay, and we cannot follow the procedure that I described. Okay? So, if the contour is pinched, then it fails, then this fails. And one of the results that one can show that this never happens when U belongs to first quadrant. Okay. But it does happen as U approaches the real axis, and that's why you have to define the value at U equal to 1 as a limit of U goes to 1. Okay, on the real axis, it may happen that contours pinch. Contour is pinched between two poles, but it doesn't happen as long as U is in the first quadrant. Okay. And this is what allows you to define the analytic continuation. This is what tells us that when you take this result on the imaginary axis and analytically continue in the whole U plane, okay, there is no singularity in the first quadrant of the U plane. Okay, so you can take this contour in any way that you like, okay, and you will reach the same value, okay, because you can continuously deform one contour to another without hitting any situation where the contour gets pinched, okay, where the deformation is not possible. Is this clear? Yes, under Lorentz transformation, what will happen is that the endpoints will move, they will rotate, but they will still remain exponentially suppressed, right? Because along this, the loop momentum integral, okay, approaches an Euclidean infinity, right? L square is negative, and that doesn't change under Lorentz transformation, right? And that's all you need to make sure that the exponential factors are really exponentially suppressed and not exponentially growing, right? Yeah, so under Lorentz transformation, so here I have said that you take the energies to be fixed at plus minus I infinity. That is not strictly necessary. You could make them rotate, okay, but not beyond 45 degrees, for example. Yeah. In fact, it turns out that to prove the equivalence of this procedure and this other procedure of deforming the Swinger parameter, okay, you have to, it's hard to do it when it's exactly on the imaginary axis, but you can tilt it a little bit and then the proof is simple. And then you add an extra bit which shows that whether you take it to the imaginary axis or a slightly tilted axis doesn't matter for this case. So I should just say that this will fail, okay, if we had allowed independent parameters U to multiply the P's. Okay, if for example you had taken this to be UI, EI, okay, where each UI is an independent complex parameter, and you made them move in the first quadrant, okay, then you may sometimes encounter situation where the contour is pinched. Okay. But as long as all the energies are multiplied of the same U, okay, then there is no difficulty in this analytic continuation. The second result is that as long as the original action was real, which you can show independently that it is. Original action is real. The anti-Hermitian part of the amplitude Okay, so I'll explain what the Cutkosky rules are. So let me give a more formal statement. Yes.
So when we, supposing we have more than one loop momentum.
Yes.
Then we are looking, I suppose we have n number of loop momenta, we are looking in a complex space of dimension 2n.
Exactly, yeah.
And you're looking at the zeros of this ki square plus n.
That's right, yeah.
So for all the propagators.
Yes.
I mean, so I'm trying to understand. So, or you're looking at places where any one of them would
Get pinched, exactly.
And so that is one equation in these one equation for u in terms of all these LIs.
Yes.
The loop momentum, one complex equation.
Okay.
But that so it's complex codimension one. I mean, so it's one equation.
Yeah. See, the point is that okay, you have many loop momenta, right? Suppose you fix all the other loop momenta. Suppose you fix all but n minus one of them. Okay. You look at the first one. Okay. And then you see if there is any possibility that it may get pinched. Okay. Suppose you find that there is some subspace of other loop momenta and u where this momentum gets pinched. You look at one loop momentum, pick any loop momentum integral, right? Look at it as a function of the other loop momentum and imagine that there is some subspace over which this gets pinched. Okay? But that doesn't mean that the contour is pinched, because now you have to ask whether the other loop momentum integral are pinched on that subspace. Right? If you could deform those other loop momenta away from that subspace, then it's not pinched. Right? So this is a condition for pinch, that each loop momentum must be pinched. Right? Either that loop momentum doesn't enter the pinch equation, right? Or if it enters the pinch equation, it must be pinched, right? So that by varying that, you cannot get away from the contour, the pinch singularity.
Exactly.
So this is what you prove is not possible.
Yeah. But, okay. No, but I was wondering whether, in general, since if we just take the whole space all at once and look at how this complex codimension one condition is changing as we move u. So isn't it possible to always avoid it because it's complex codimension one?
So on the when u is real, right, there are certain examples where the contour is pinched, right? And I'll discuss one example where that is the case. So there are certain examples where all loop momentum integrals are pinched, right, for certain values of u. So basically the way we prove this is assume there is a pinch, right, so which will have certain conditions, because various loop momentum integrals have to be pinched, right? So there are on-shell conditions, and then you show that there is always a deformation which takes you away from the pinch. Okay, that you can simultaneously deform all the loop momenta which goes away from that singularity. without hitting any other singularity, and that's the way one proves that it's not possible in the as long as U is in the first quadrant. But this fails when U becomes real. Okay, so what is Cutkosky rules? Okay, so let me make this statement a little more precise. Okay, so suppose A is the amplitude. Okay. So what the precise statement is that I times A minus A dagger. Okay, dagger just means Hermitian conjugate of the amplitude. Okay, you replace the incoming states by outgoing states and reflect all momentum and so on. I times A minus A dagger is given by sum over all cuts of the diagram. In fact, this the result is valid diagram by diagram. So instead of saying A is the amplitude, let's say A is the contribution from a given diagram. Okay. So what do you know sum over all cuts? So take some Feynman diagram. So cuts, so suppose take a Feynman diagram. So incoming states, so you use the notation that incoming states on left, outgoing states on right. Okay, so take some complicated process. Okay, some complicated process. Okay. And a cut means just draw a line, okay, that divides the left half and the right half. Okay. The line may be like this, okay, or another possibility will be something like this, okay, something like this. Any line that divides the left half and the right half, okay, is a cut. So the rules for computing cut diagrams, rules, okay. First, okay, you replace 1 over k square plus m square factor of a cut propagator by 2 pi I delta k square plus m square. Second, the amplitude on the left to the left of the cut, usual Feynman rules. And amplitude to the right of the cut is given by Hermitian conjugate of usual amplitude. And nothing happens, no extra contribution from cut external propagator. Okay, so this rule is for cut internal propagator. Let me write this. Okay, so for example, in this There is no colored chalk, I guess. Otherwise, let me draw the cuts using colors. So if the cut is like this, then for each of these, the 1 over k square plus m square factor you replace by 2 pi I delta k square plus m square. And then this part is the same, the ordinary amplitude, this part is the complex conjugated amplitude. If the cut is like this, okay, then for these two lines, you again use that. Oh, I should have said something else. There is another factor. Okay. There is a theta of k0. Okay, so let me explain this here. So theta of k0, so k0 is the energy flowing from left to the right of the cut. Okay. So for this there will be delta k square 2 pi I delta k square plus m square times theta of k0 for this, this and this. For this line, if the cut is like this, okay, then for this line there will be 2 pi I delta k square plus m square theta k0. For this line also there will be a similar factor. Okay. K is now the momentum that is flowing this way and this way. Okay. But for the external line you don't make any special substitution. Okay, external lines are removed anyway and they continue to be removed. So this is what one means by Cutkosky rules. Okay, and what one can prove is that with the procedure that I have described, okay, of this contour integrals, okay, the amplitudes satisfy the Cutkosky rules. Okay, the anti-Hermitian part of the amplitude is given by these rules, that you take a diagram and its imaginary part or its anti-Hermitian part is given by sum over all the cuts of this diagram. Okay. So the proof is combinatoric, it's a long proof and I will now try to describe how the proof goes. Maybe near the end of today's lecture I will give an example, okay, which may at least make some things clearer. Okay, but this is a statement of Cutkosky rules. Is that clear? Okay. Now before I go on, okay, let me just say a few words about why this is important for unitarity. So suppose S is the S matrix and normally one uses the T matrix or the transition matrix. Okay, I will use S equal to 1 minus IT. Okay. So if you use S dagger S equal to identity, which is the statement of unitarity, okay, this translates to T matrix as I times T minus T dagger equal to T dagger T. And this I can write as sum over n, T dagger n, n T dagger, n T. Okay. So if we calculate the matrix element between T and T dagger, it's sum over n, A T dagger n, n T. Okay, this is a statement of unitarity. Okay. And Cutkosky rules establish unitarity in the following sense, okay, that what you are calculating is I times A minus A dagger. So left hand side is directly what you are calculating, I times T minus T dagger, right? Amplitude by amplitude, it's related to T. T of course is the sum of all the amplitudes. okay, but it's I times t minus t dagger. So the interpretation of the right hand side is that this part, okay, is like, this is like the sum over intermediate state, a cut, okay, whatever propagators are cut are the ones which represent physical states, physical intermediate states, okay, the n. So they have to be on shell, okay, and that's what is reflected by the fact that you put them on shell by this delta k square plus m square, okay. The sum over states of course has to be over on shell states, okay, in this sum over n. Okay. So you have a matrix element, okay, on this side times the complex conjugate matrix element on this side, okay, and that's what is reflected here in this amplitude over here. Okay. So that's roughly the way Cutkosky rules are related to unitarity. Okay, but there are certain steps that you have to follow before we can actually establish unitarity from Cutkosky rules. Okay, and so I'll describe some of them today and then the rest in the next lecture. Okay, are there questions? Okay, so basically once you put this delta k square plus m square, then the integral of d4k delta k square plus m square basically becomes a phase space integral over the final states, right? And that phase space integral is what is inherent in the sum over n here. Now, as I said, there are some issues in going from the Cutkosky rules to unitarity, some of which were resolved long time ago in the old days of field theory, okay, and that's the part I'll describe now, okay, and some of them are specific to string field theory, okay, which is what I'll describe next time. Okay. So here you see this is an arbitrary diagram that you are cutting, okay. Let's consider the following situation. Okay, let's consider the situation where you have some diagram. Okay, we will just focus on this. Okay. There are external states coming in from here. We don't care what these blobs are. Okay, our focus will be on this line over here. Okay, this is an internal line with some self-energy insertions. Okay. So you say now let's consider that we have a cut like this. Okay, and suppose k is a momentum flow along this. Cutkosky rules are blind. It just says that you sum over all cuts. Okay, so in particular you have to cut. We have to sum over a cut like this. Okay. Now when you cut this, we insert a factor of delta k square plus m square. Right, because this line is cut, this momentum is also k. Okay. But you can see that once you insert delta k square plus m square, okay, this leg of course is just 1 over k square plus m square. This is not cut. Okay. It will be multiplied by several factors of 1 over k square plus m square. Right, this is also 1 over k square plus m square, and so on, and some from here. So this is of course infinity. Okay. So if you naively apply Cutkosky rules in a diagram like this, okay, you will get infinite answer once you have set one of the intermediate lines on shell. Okay. So what one has to do in this case, okay, to deal with situations like this, okay, is that we don't analyze one diagram at a time. Okay, but imagine that we ultimately have to sum over all cuts. Okay, so we sum over cuts of this diagram, okay, then other cuts which differ from this, just by being rest of the cut is the same, Okay, they pass through the same lines, except that on this line you sum over all possible ways of this line going into either here or here or here or here, also through this 1pi diagrams and so on. Okay, you sum over all the cuts. Is this clear? So if you do that, okay, then this part of the diagram is the same, is common between all of them. Okay. So what we can ask is that what is the effect of summing over the cut passing through all of these graphs? Okay. And by applying the same Cutkosky rules, okay, on just this particular sub-diagram, okay, you will conclude that this result can be expressed as, let me call this full, either a cut passing like this minus, or let me write it as imaginary part or minus the other anti-Hermitian part of the full propagator, right? Because after all, this is sum over cuts. Okay, if we apply Cutkosky rules in the reverse, right? Sum over all cuts of a diagram is the imaginary part or the anti-Hermitian part, right? So here all you are doing is you are keeping this part separately. You are just summing over all possible cuts of this, and so this must be anti-Hermitian part of the whole amplitude. Is this clear? So this full means multiple insertions of 1pi amplitudes. Okay. And then you simply sum over all such insertions. Okay, now instead of working on a given loop, okay, you sum, so this full now you replace by full, you now replace by this plus okay, so you have to reorganize your sum by taking the self-energy insertions on the internal lines and resumming it, okay, as 1 over k square plus m square minus the 1pi contribution. Okay, this is a standard way you resum self-energy insertions. But now we are not talking about self-energy insertions on the external line. Okay, this is self-energy insertions on the internal line that you are resumming. Okay, because otherwise the cut diagrams will be individually divergent. Okay, so the sum over all these cuts is given by imaginary part or the anti-Hermitian part of this. Okay, yeah. Are there questions on this? Yes. Pardon? Well, they need not be the same in a given diagram, okay, but you now sum over all possible diagrams, right, in which case each 1pi is the sum of all possible 1pi amplitudes up to a given genus order, right. So then they become the same, and that's when you can do this resummation. Okay, so yeah, so if you insist on working diagram by diagram, right, then this procedure doesn't work, right. That's why, just like for the external legs, you have to actually sum over all diagrams, okay, all insertions of all 1pi amplitudes, okay, and then apply LSC. The same you have to do for the internal lines when you do discuss propagators. Okay, so now there are two cases that you have to consider, okay, which has slightly different treatment. Okay. So the case one, so let's call this a full propagator. Okay, let's call this delta. We are trying to calculate the imaginary part of delta. Case one is when this renormalization, okay, doesn't make the particle unstable. okay, the particle still remains stable, which means that the pole that you get in delta is still on the real axis. That's what happens for stable particle mass renormalization, right? Electron mass renormalization, for example, right, shifts the electron mass but doesn't give an imaginary part. Okay. So in this case, delta is 1 over k square, or maybe z, this is the wave function normalization, k square plus m square minus I epsilon. Okay, so this minus I epsilon basically comes from taking u goes to 1 from first quadrant. Okay, this you can show. I am not going to the details, but this is the same reason that weak rotation generates this rule, right? In normal quantum field theory, weak rotation gives this a minus I epsilon, is the same here. Okay, I have defined the amplitude from as the limit from the first quadrant, and effectively that gives this minus I epsilon. So in this case, imaginary part of delta will be just 2 pi I z delta k square plus m square. Okay, not imaginary part of delta, but delta minus delta dagger. Delta minus delta dagger. Okay, I am taking here is one dimensional case. So delta dagger is the same as delta star. Okay, just take the this minus its complex conjugate, and using the fact that 1 over x minus I epsilon is principal value of 1 over x plus I pi delta x. Okay, we can get this. Okay. So this basically tells us that if there is a cut propagator in the Cutkosky rules, if there is a cut propagator, okay, where the line that flows through is a stable particle, okay, its pole is on a real axis, okay, then you replace it, you follow the usual procedure for Cutkosky rules of replacing 1 over k square plus m square by this, okay, except that now you have to use the renormalized mass over here. Capital M is the renormalized mass, okay, and you have to put the appropriate wave function renormalization factor. Okay, so a cut propagator, okay, if you draw a line like this, okay, this from now on will signify for a stable particle, okay, the full propagator, okay, even though you may not draw it, it's the full propagator, okay, and what you insert corresponding to this is 2 pi I z times delta k square plus renormalized mass square. Okay, and now we'll never introduce any 1 pi. We will not introduce any 1 pi on this or on this. Okay, because the whole thing has been resummed already, okay, to get to this form. Okay, so on this propagator now there will be no 1 pi insertions. Okay, this will be like external legs. Okay, and hence there is no further divergence of the kind that you saw. Okay, these kinds of divergences are not there anymore. Okay, with this rule. Is this clear? Okay, now the case 2. Delta is z over k square plus m square minus I gamma. Okay, particle has become unstable. This gamma is something that comes from loop contribution. Okay, this is the signal that if m square becomes unstable, this is the signal that the particle is actually above the threshold of producing some other lighter particles. In this case, we can basically forget about the I epsilon. You can also add a minus I epsilon, but it makes no difference, right? Because there is already a gamma. So now you can write delta minus delta dagger. Okay, maybe I should also write down what this. So this will come from the following structure of 1 pi. So 1 pi is m square minus m square z inverse plus 1 minus z inverse k square. Okay, plus higher order terms which you don't care at this stage. Okay, in general, of course, it's a complicated function of k, right? And you are looking near the pole. But let's look at the simplest situation. Okay, so why is this so? Because you can see that if we substitute this, that expression for 1 pi here, you will get back the z over k square plus m square. Sorry, m square minus I gamma. Yeah, looking in the vicinity of the pole, but you can do a more general analysis. So now delta minus delta dagger can be written as z over k square plus m square minus I gamma. I'll just write it in a somewhat suggestive form. Gamma is real by definition. Okay, these I'll leave as an exercise for you to check. This is given this delta minus delta dagger will be you subtract k square plus m square plus I gamma, right? Then complete the square. Okay, and you can write in this form. So this I have written because this now can be given a diagrammatic interpretation. Okay, so what is the diagrammatic interpretation of this? So this is full 1 pi full the cart passing through 1 pi. Okay. This part which is on the left, okay, is this one. Okay, to the left of the amplitude is the same rule. Okay, this is a full propagator. To the right of the amplitude is a full propagator. Okay. And this one I gamma, okay, you can see the 1 pi, the only imaginary part of the complex part comes because of the I gamma. Okay. So the cart passing through 1 pi, okay, if you take sum over all carts passing through 1 pi, that's the imaginary part of 1 pi, right, or the anti-Hermitian part of 1 pi. But again, the same Cutkosky rules applied on this. Okay. So that will be I gamma minus H star. Okay, that's minus I gamma. Okay, and that exactly matches delta minus delta dagger. Okay, so this is just to show how to interpret delta minus delta dagger as a cart diagram again. So then of course it will cancel. Oh, minus I gamma, let's see. I think when you take the difference, it's 2 I gamma. So basically delta minus delta dagger is 2 I gamma z, right, divided by this times its complex conjugate, right, and that's what I'm writing. So this difference is 2 I gamma, right. The one z inverse cancels is z, right. So I think delta minus delta dagger is given by this. Yes. Yeah. Yes. So this is this, right, and this one is this. Because you are supposed to complex conjugate the amplitude to the right, right? If you complex conjugate the amplitude to the right, then the minus I gamma becomes plus I gamma, right? That's the reason why it has become plus I gamma. Okay, and then the cart passes through this 1 pi. Okay, so this then means, okay, that you can translate this to the following rule, okay, that for an unstable particle, okay, the cart never passes through its propagator, because you see this cart, okay, is passing through the 1 pi amplitude which has other particles flowing through, okay, not the one that we started with which has become unstable. Okay. So the rules then can be summarized by saying that for stable particles, okay, you let the cart pass through a stable particle, okay, and when it passes through a stable particle, you have to use the full propagator and use this rule, okay, and never let the cart pass through an unstable particle propagator. Okay, so the cut never passes through this, for example. This would have been unstable particle propagator. Okay, and this in fact fits in nicely with the what we expect for unitarity. Okay, because in unitarity, when you have this sum over here, right, this sum over n should include only stable particles, because stable particles are the only acceptable final states, right? Unstable particles are not asymptotic states, right? So they shouldn't enter statement of unitarity. Okay, they may enter statement of unitarity in a perturbative sense, in the lowest order in perturbation theory, but once you go to sufficiently high order, okay, when you see their instability, okay, then the sum over final states should only include, sum over the intermediate states should only include stable particles, okay, and that's what this is showing. Okay. Even though to begin with, the initial derivation of Cutkosky rules, okay, as a sum over all cuts of a given diagram, that didn't care about whether you are passing through unstable particle or stable particle, you just sum over all cuts. Okay. But now what we are saying here is that you can reorganize it, okay, in a way where you sum over cuts of stable particles with this wave function renormalization factor and the renormalized mass built in, okay, and you never sum over cuts of unstable particle propagator. Is this point clear? Okay, so this is one of the issues which is nicely resolved. This is a general field theory result. As I said, you can find it in this diagrammer by Teuton Veltman, which was written in the 70s. Okay. But there is still another issue which is left, okay, and which has to do with the fact that when you apply this to string field theory, okay, we will be applying this to string field theory in the Siegel gauge. That's why you have developed our perturbation theory. Okay. And so the sum over states that we will get, okay, will be sum over all states in the Siegel gauge, which propagate in the Siegel gauge. Okay. But you know that string theory is a gauge theory, okay, and not every state in the Siegel gauge is a physical state. Okay, it may correspond to a pole, but it need not be a physical state. Okay, it's like QED in the Feynman gauge, right? QED in the Feynman gauge, okay, has of course physical states in the propagator, but also unphysical states propagating. Okay, unphysical states, ghosts, everything, right? In the Feynman rules, you have not only the original classical fields propagating, but also the ghost for propagating, right? So you have to make sure that while Cutkosky rules, okay, so this up to this point, right, we have said that the stable particles should be included, unstable particles shouldn't be included, okay, but nowhere here we have seen that the unphysical particles shouldn't be included, right? If the hosts are stable, they should be included as far as this analysis is concerned. Okay? But to really prove unitarity in string theory, you have to ensure that the unphysical particles also don't propagate, right? So somehow in this sum, only the physical states should appear, okay, and not the unphysical states or host states. Okay? So that's what we will be proving next time, okay, that even though to begin with, we have all states in the Siegel gauge in this sum, okay, eventually only the physical states contribute to the sum. Okay. But what I plan to do in the rest of today's lecture is to give an example, okay, because some of the things may look somewhat abstract. So in particular, this contour deformation procedure that I described, okay, I'll show explicitly by an example how it works. Yes?
So when you cut this 1 pi, there's unstable particles within the 1 pi, you don't cut it.
No, because if there are unstable particles in the 1 pi, you apply this again. Yeah, you do it recursively, right? So eventually you cut only the stable particles. So that's the rule, that you cut only the stable particles, and for the stable particles you have to use the full propagator.
One normally shows this thing that the unphysical states don't contribute this by using some DRSTI.
What identity? Yeah.
So probably more generally this PD type of.
Yeah. So we'll have to use some analog of that in string field theory, and that's what we'll see next time. That how you can use the word identities of string field theory to prove that all of these decouple. Right? But these will involve, these will include also the renormalization effects. right? Because these will be the word identities of string field theory in the shifted background, right? Where we have already taken into account the normalized effects. Because now you see that because what enters is the full propagator, okay, is a renormalized mass, and so we can now use for our analysis the full propagator that we derived last time, right? That is the propagator which will enter in the cutting rules. Okay, so you have to work with that propagator and then show that the unphysical states decouple from there. Okay, in fact, you have to first define unphysical states appropriately, and then we will see that they decouple. Okay, so example. Okay, so this of course will not be really necessary for next time, okay, because for next time we will really need these general results, but I thought it's good to give an example, okay, to see what really is going on here. Okay. So the example that we'll be considering is a simple Feynman diagram of this kind, okay, and I'll consider just a scalar field theory, okay, with a Feynman diagram of this kind. Okay. So this external particle, okay, is what I call a heavy particle. Okay. So this particle has mass m, and what propagates in the loop has mass small m. Okay. So some momentum p is coming in. Okay. This is L, this is p minus L. So let me write down the formula for the mass shift. So this is a mass renormalization diagram, right? So this diagram will tell you how much the mass gets shifted, okay? And here is the general structure, okay? So there is a constant B which basically comes from the couplings at these two vertices, and we will use D dimension. Let me write it and then I'll try to explain these various factors. Okay, so this is the general structure. So L is the loop momentum. Okay, these are the exponential suppression factors. Okay, I have just included them to mimic what happens in string field theory. Okay, although I'm not using here sub states, I'm just assuming that there's only one state that is propagating, and these are the usual propagators, okay, which are coming from these two. And I'll take P to be S frame, so P will be M0. Okay, this is just to simplify some formulae. Yeah, I'm using the same A, but it's not necessary. You could use also different A's. In fact, what is going to happen is that from this vertex there is separation, from this vertex there is separation. Right? As long as these two are the same particles, by symmetry they are the same A. But you could have chosen to be M1 and M2, in which case these could be different A's. Okay, so this we have to now continue to UM0. Okay, U is that complex parameter. Okay, that's the one that we'll use for analytic continuation. So let's look at the poles. So poles will be at L0 equal to plus minus square root of L square plus M square, okay, and then UM plus minus square root of L square plus M square. Okay, and we will give them some names. So let's call this pole Q1, this as Q2, this as Q3, and this is Q4. So in the U plane, sorry, in the L plane, L0 plane, this is L0 plane. Okay. Q1 and Q2 are on the real axis. This is Q1, this is Q2. And you have, for U imaginary, okay, if U equal to imaginary, okay, this is where I am drawing this, then you see that these poles, okay, have some imaginary part which is given by UM, and then they are symmetrically situated around the imaginary axis. So something like this, Q3, Q4. Okay. And the integration contour is running like this, because for U imaginary we said that we will start with the L0 contour running along the imaginary axis. Okay. So you can see that this integral should be perfectly well defined as long as you define the L0 contour running in the imaginary axis, okay, because these exponential suppression factors makes everything convergent at infinity, and the poles are all away from the imaginary axis, right? So there is no ambiguity in defining this integral. And now you see, the important information that you have to gather from here is that originally, with respect to the contour of integration, Q1 and Q3 are to the right, and Q2 and Q4 are to the left. Okay, and if during the deformation of U we do not allow the poles to cross the integration axis, okay, this feature has to be maintained. Q1 and Q2 should continue to be to the right, and Q2 and Q4 should be to the left. Okay. So now consider the limit U goes to 1. Okay, same pole locations, but now everything is on the real axis, as you can see. So in the L0 plane, we have two situations. Okay, let me write down the first situation. Okay, then I'll also see. So Q1 and Q2 of course are U independent, so nothing happens to them. But we have Q3 and Q4. This will be the situation. So you see here Q4 is to the left of Q1, right? Q4 is less than Q1. So Q4 is less than Q1, okay, and U is 1 here. So Q4 less than Q1, so Q4 had this minus sign, so that corresponds to M is less than 2 square root of L square plus M square. Okay, so in this case the contour the poles are arranged like this. So how will the contour be? You see, the contour has to start from minus I infinity, end at plus I infinity, because the end points we are not moving. Okay, and the contour has to maintain that Q3 and Q1 should be on the right, and Q2 and Q4 will be to the left. Okay, so the contour, let me draw this by. The contour will be now like this. Okay, so you see that you cannot keep the contour along the imaginary axis, because if you had kept it along the imaginary axis, then somewhere Q4 will have to cross. Okay, Q4 cannot come from the left to the right. Okay, so as Q4 is pushing the contour has to be deformed. The second case, when Q4 is larger than Q1. So here is Q2, Q1, and here you have Q4 and Q3. Okay, you can follow what happens to the contour. Okay, you can start from this case and see what happens when Q4 becomes larger than Q1. Okay, to see how we should deform the contour, it's important to remember, you see that Q4 has this plus UM. Okay, and U always is in the first quadrant, right? You always have to think of this U as coming from the first quadrant. So Q4 then always has a small positive imaginary part. That's how you should think of it. Okay, whenever in doubt. So if Q4 has a small positive imaginary part, then it's a little above the real axis, and then as it moves past Q1, it drags the contour with it. Okay, so the contour will look like this. Okay, so this is the procedure for doing the integrals in this case. Okay. And you see that the contour is pinched as Q4 and Q1 come together, right? When Q4 actually crosses Q1, then the contour is actually pinched. Okay. And there you have to be a little extra careful in defining how to this integral, that you have to first add a plus I epsilon to Q4 because Q4 has this U built in here. Okay, so you should always think of U having a small positive contribution. Okay, so Q4, you see when Q4 approaches Q1, you have to define the contour by taking Q4 to be slightly above Q1, okay, and then taking the limit at the end. Okay. So let me describe now how to calculate the imaginary part of this integral. Yeah, so the U goes to one limit has to be taken at the very end, right? Yeah, because you always define the amplitude first as long as by taking the U in the first quadrant, right, with positive imaginary part, and at the end of the calculation you take U to 1, right? But in cases where Q4 and Q1 are well separated, it doesn't matter, right? You can take U goes to one limit even in the intermediate stage, okay? But you have to be careful in when they're coming close. Okay. So let me just say briefly how to evaluate this integral. Okay, if you are interested in the imaginary part of the integral, how to evaluate this. Okay. So what you can do is that in both of these, okay, you can deform the contour through Q4, okay, and take one contribution where it just lies along the imaginary axis. Okay, that's one part, and then you pick up the residue from Q4. Okay, this you can do for both. Okay, is that clear? Just write it as sum over two contours, one along the imaginary axis, the other one is along Q4. So this gives you delta m square as a sum of two terms. Okay, so I1, let me write what it is. This is the imaginary axis integral IB integral This integral is perfectly finite because the L0 integral is along the imaginary axis, so this exponential suppression kills the divergence from infinity, and you can clearly see that there is no pole on the imaginary axis, so there is no, you get a perfectly finite integral. Okay. But this you can also show is real. Okay, it's a little, well, it's not very tricky. Okay, you have to, if you complex conjugate, this changes sign, these to change sign, and what you have to do is to change variable from L0 to L0 star, and using that you can show that this complex conjugate is the same as itself. Okay, so this doesn't give any contribution to the imaginary part, okay, but this does contribute to the real part, which is a finite contribution. Okay. In a normal quantum field theory, this will be divergent, okay, because one loop mass transformation typically is divergent because of ultraviolet divergence, but this is perfectly finite. And that's what happens in string theory, that in string theory the mass, there is mass normalization, but it's a finite mass normalization, okay, because of these exponential suppression factors. Okay, the second integral, which is the pole contribution, okay, that's the residue from this pole. So I2 is IB times 2 pi I, this is the 2 pi I of the residue, then 1 over 2 pi because there is a dk0 over 2 pi, sorry, the dl0 over 2 pi, and then integral d minus 1l. So this is a step function. It basically is a reflection of the fact that when m is less than this, okay, q4 is actually already to the left, so you don't pick up a residue. Okay, the contour integral, you can deform the contour to imaginary axis without picking any residue at all. So that's this step function. Pardon? No, m minus, at m equal to 2 of this, q4 reaches q1. Right, but this is the condition that q4 reaches 0. Yeah. So once q4 goes to this side, right, then the residue contribution is not there, right? You can just deform this contour to straight to the imaginary axis without picking up any residue. So that's coming from the step function. Then exponential minus a So this is all these factors come just from evaluating the residue. Okay, so the important point here is this I epsilon. Okay. This I epsilon comes from the fact that I have to take u to 1 from the first quadrant, right? So you had replaced the P0 by right? And now you have to take the u goes to 1 from first quadrant, which means that adds to m a positive part, right? And that's what this is saying. Okay, so this is like I could have written as and taken the limit u goes to 1 from the first quadrant, right? That's equivalent to this. Okay. So this has an imaginary part. Okay, this I and this I gives you -1. Okay, so there is no imaginary contribution from here. So the imaginary part of I2 basically is coming from here. Okay, that this factor has the imaginary part of this is pi times delta 2 square root of L square plus m square minus m. Right? It's this inverse. Yes, thank you. Okay, it's that 1 over x minus I epsilon is principal value of 1 over x plus I pi delta x. So this is this I pi delta x term. Okay. This is the way you calculate the imaginary part of I2. Okay. And I'll leave it as an exercise to check that it's given by the Cutkosky rules. This is the threshold value, exactly. Well, and actually the way we are doing it here is we always work at fixed loop moment, fixed spatial components of loop momenta, right? So this is what will normally not called the threshold. This is a place where there is an on shell, where the intermediate states can go on shell, right? Threshold is where it starts becoming on.
2m.
Yeah, exactly. When m equal to 2m, right? Exactly, right? But this is, I mean, you work at fixed loop momentum, so the imaginary part comes from whenever it goes on shell. Okay, so exercise, check that delta m square minus delta m square star, okay, which is basically 2i times this imaginary part. Okay, if you take delta m, so I2, this is a delta m square, I2 is one of the contributions to delta m square. So this is given by this cut diagram. This is the thick line. Okay, and in more concrete expression, it's given by IB integral actually it's not delta m square, but there is a factor of I, right? It was I times t minus t dagger was given by t dagger t. Okay, so this is the general Cutkosky rules, right? That's I times, let me just make sure that I have got the sign correct. Yeah, I times t minus t dagger, that's right. So I times delta m square, my delta m square star should be given by the sum of what cuts. In this case, there is only one cut, okay, which is relevant. And the cut means that you take the original amplitude, but the 1 over L square plus m square factor you replace by 2 pi I delta L square plus m square, and similarly 1 over p minus L square plus m square factor, okay, because both lines are cut, you replace by 2 pi I times delta p minus L square plus m square. Okay, so you can easily check that this and these are equal. Yeah, yes, sorry, thank you. There is theta L0 and theta p minus L0, okay, because that's also part of the cutting rules.
The imaginary part, if you use the delta function there, the exponentials cancel out, is that right? Or?
No, I think the exponentials, let's see.
Because we don't need the subsystem.
Yeah, I think exponentials will cancel out because both lines are on shell, right? So for the imaginary part, because both lines are on shell, so yeah, yes, the exponentials will cancel out. But it's still a finite contribution. Yeah. Yeah, because imaginary part is the product of two on shell amplitudes, right? So there, of course, the exponential factors have been chosen so that on shell they don't affect, they don't contribute. So exponential factors will cancel out in the imaginary part. Yeah, in the interior, exactly. So when you cut it, on the cut lines, the exponential factors will cancel out, but in the interior, of course, the exponential factors will still be there. Yeah. Okay. So as I said, the general proof is more complicated, okay, but it basically follows on the line of argument that you, by brute force, you try to calculate the imaginary part of an amplitude, and you basically use various iterative scheme, right? You prove various independent results, okay, and then show that the combination of those results imply that the imaginary part of the amplitude is given by the sum over cuts to all orders. Okay, so I think I'll stop here, and so next time I'll do the final story to show that in the context of string field theory, okay, how all the extra states cancel out and you are left with physical intermediate state contribution. Some? Yes, so okay, the point is what? We are assuming that there are certain number of non-compact dimensions which are flat, because that's where you define your S matrix, right? But then there is some compact dimension which is described by some worldsheet conformal field theory, right? Which as long as it's unitary, we don't care what it is. Right? The unitarity is needed because we have assumed that the string field theory action is real.
Let me ask my question.
Yes. Yeah.
So, in this theory also there are gravitons. Right?
Yes.
So I can talk about very high energy scattering
Of gravitons, yes.
Now, standard law says that form a black hole.
Yeah.
And,
But that will happen you will not see order by order in perturbation theory, right? Order by order in perturbation theory, you can define graviton scattering amplitude, right? Without forming a black hole. Exactly, that's right. Yeah.
my question is about the loss of unitarity issue.
Yeah, I think you cannot use perturbative string theory to address that issue, right? Because to see the black hole formation, you have to sum over infinite set of diagrams, right? I mean, someday it may become possible how to understand, the sum and see how unitarity comes about. But this is defining string field theory order by order in perturbation theory, right? And to any given order in perturbation theory, you will not see that issue coming in here, right?
In some sense, this theory is not complete.
Yeah, so because it's not non-perturbative, right? Exactly.
Suppose you were to sort of take this as a non-perturbative action.
Yeah.
And then, I mean, in conventional field theory, when you have that, you can prove unitarity because, okay, again, you need a Hamiltonian.
Exactly, yeah. Yeah.
Here, again, I guess the problem will be.
There is no Hamiltonian, exactly.
To
Yeah.
obtain the Hamiltonian
Yeah.
and show there's a symmetry of
Yeah.
Like the perturbation theory takes on, you can see directly also in the Polygraph formation, right? Because you go to very high energies, this is a Grossman decay.
Yeah.
They compute the torus saddle point, and that's explicitly smaller than the sphere saddle point if you go to high number.
Yeah.
Half that.
Exactly. So at high energy, certainly you don't expect perturbation theory to be valid here.
And you can explicitly see.
Yeah. Okay. Yeah, so I guess the general philosophy here is that, to wherever you can trust perturbation theory, right, you should get unitarity. If you find that where you can trust the analysis, right, there is some violation of unitarity, that is really bad news for the theory, right? If in some regime we cannot do the calculation using this formalism, and in that regime you see that unitarity is violated, then you don't care because, then you know that there has to be something else.
Do you want to comment about causality? Usually the analytic properties is what in quantum field theory one.
Yeah, we have been trying to understand causality, but we have not really gone to to any extent that we can make a definite comment. Right? Because in quantum field theory, people use various arguments for causality, but none of them are really purely based on Feynman diagrams, right? Whereas here, even if you want to prove perturbative causality, right? Suppose you want to show that to any given order you preserve causality, you have perturbative tools, right? And the usual proofs that people give in quantum field theory always uses some axiomatic results from field theory, which are not based on perturbative theory. But the idea is that we translate those proofs into a perturbative proof in quantum field theories, and then you can see how we can generalize to string field theory.
Right, so you say the same thing about this Bogoliubov causality, there is a particular.
Yeah, see, Bogoliubov causality, yeah, there I don't know, because I don't know how to work in the position space here, right? Whereas here what we are talking we mean by causality is basically analyticity, right? The question is whether this theory has analyticity by which you can say take from S channel diagram or T channel diagram. Okay?
But should one be able to answer this Camanio, Maldacena, whatever thing you do, 2 to 2 graviton
Scattering, yeah.
and see whether, so this includes all the higher derivative corrections.
I agree, yes.
And that whether there is some time, I mean the analog of a phase
Time delay, yeah. So I think one should be able to translate that to momentum space because it's a perturbative result, right? Yeah. So one has to translate this to a specific statement about the momentum space Green's function or amplitude, right? And then prove.
The phase shift is positive. I mean something.
Exactly, yeah.
Yeah.
Yeah. So I think that should be possible. It's just that one has to develop the tools of translating all of this into the momentum space because understanding position space statements is hard in this language, right? But where you understand position space statement, we can convert in principle to momentum space, right? And then we can try to prove the corresponding result.
The time delay statement you can talk in momentum space.
That's right, exactly.